So let's start. So welcome everybody. It is my pleasure to introduce our second invited speaker for today, Professor Eduardo Sany from PUC Rio. I know Eduardo for long and I had also the luck to be among his co-authors, so I followed his career, his achievement and also the prizes he got. Already as a teenager, Eduardo managed to bring home a bronze medal in the International Math Olympiad. He got his PhD from PUC in CS, and his thesis was awarded the first prize in the national competition of the Brazilian Computer Society. His research activities started in the area of combinatorial search, algorithmic aspects of decision tree construction and optimization. He is a main expert in these areas, and he has published several fundamental results that have appeared in top venues like Stock, SODA, Journal of ICML, ICAL, including a Best Paper Award at ISAC 2015. More recently, he became interested in machine learning, and he has been working in clustering and in the emerging area of machine teaching. And his results also in this area have appeared in flagship conferences like ICML. Eduardo has the ability of spotting new, exciting and challenging questions in new areas as well as in classical areas, sometimes also in fields where it would be surprising to expect that something new can be said. So that's why I'm thrilled to hear what he's going to tell us about this research, his recent research in explainable clustering. So please, Eduardo, take the stage and let me remind the others to mute their mic. And so for the questions, you can either drop them in the chat or I will select some and then Eduardo can answer also online if you want just interrupting. Okay, so please, Eduardo.
Thank you very much, Nando, for your kind introductions, the organizers for inviting me for this great conference. It's an honor and a pleasure to be here. My first slide is a bit of history, just one slide. In fact, I was one of in the beginning of the century, I was very involved with Latin. I went to many conferences. And in 2008, I was one of the organizers. And we didn't have COVID at that time, but we had this, just a minute, yeah. We had this highly undesirable mosquito called dengue. And we got emails from different people saying that they didn't come. We thought about canceling the conference. But at the end, fortunately, everything was good. We had very active members of Latin America community. I met Marcos, for instance, here, some other people here, great invited speaker as Bob Tarjan. And at the end, we had even a boat excursion and even the dolphins show up. So I think it was great, good memories. But, well, after some history, let me go to the business. So, okay, my talk has to do with machine learning, which is a very active area nowadays. There are big conferences, a lot of research in industry. And the reason for this activity has to do with some striking applications. Applications in computer vision, natural language processing, and behind these applications, there are very powerful methods. Some recent breakthroughs, they are very effective, but many of them are hard to understand. And these methods are taking decisions that affect our lives. So, well, explainability is welcome. So explainable methods, methods that we can interpret and explain to other people. And the focus of my talk today is about explainability on clustering methods. I'll not spend a long time explaining why clustering is important. Well, there are a lot of applications in data analysis. In the theory community is one of these problems that are used as a test bed for developing new algorithm techniques. There are many papers about clustering. Okay. So the clustering problems that I'm going to consider, they fall into this framework here. So it's hard clustering. We have a data set with endpoints, and we want to find K groups, split this point into K groups, optimizing some given criterion F. So this is the goal of our problem, of the problems I'm going to consider. And in the explainable version, in addition to the we have this additional requirement that the partition must have a simple explanation. It should be easy to explain how each group is built. That's the idea here. So let me illustrate it with an example. Okay, we have here, let's say, points in two-dimensional space, and we want three groups. So we can run let's say, a clustering algorithm, and we come up with these three groups. But, well, a clustering like that, it's not easy to explain. And what we try to do here is the following. We will, we want to come up with explainable clustering. And for that, we're going to use decision trees. Well, decision trees are a very popular tool in machine learning. And one of the reasons for that is that it provides a simple explanation. It's easy to understand why a decision tree is, for instance, making a classification. And it can be used also for clustering. So the idea is here. At the root of the decision tree, we have a test, and this test split our data set into two regions, one on the left and the other one on the right. Okay, so if this is a leaf, okay, so this leaf here corresponds to this region. And then in this, for the left points, we can apply another test that will divide this region into two new groups. So this is the kind of clustering that we obtain. And in terms of explainability, it's easy to explain the reason of each cluster. For instance, the blue cluster corresponds to the points that feature 1 is smaller than 70 and feature 2 is larger than 40. So we're gonna, so the clustering problems that I will consider, they fall into this framework here. We are inspired by a paper that appeared last year in ICML. So as an input, we have the data set, K, the number of clusters, the optimization criterion F, which can be this minimizing the sum of the square distance or other criteria. And we want to partition our set into K groups, optimizing F, but using a decision tree with K leaves. So each of the leaves of the decision tree will correspond to a group. So this is the kind of problem that I'm going to discuss. And our main question here is, how much do we pay if we want to have explainable clustering? So what is the price of explainability? And one formulation for this question, to have a rigorous notion of the price of explainability, we use this formula here. So the price of the explainability for a certain problem, clustering problem we are considering, is given by the max over all instances of the problem of this ratio here. So this ratio considers the optimal explainable clustering for instance I, and the optimal unrestricted one. So this is for minimization problems. And for maximization problems, is pretty the same. We just need to switch the numerator and the denominator. So this is for maximization problem. So we want to understand how much do we pay to obtain an explainable clustering. Okay, the way that is defined, the price is always larger than 1. So we want to have bounds for this price. And in this research, we are considering some optimization criteria, some popular ones, as the criterion for the K-center clustering problem, for K-medians, for K-means, for the maximum spacing. So we are covering worst and average case metrics, intra and interclustering metrics. And about the maximum space, it is interesting that it is the single linkage, which is basically the minimal spanning tree algorithm. It's widely used for hierarchical clustering, and it optimizes this maximum spacing. So these are the criteria that at least some of them I'm gonna discuss. And as I mentioned before, this research is inspired by a result that I saw in the last ICML from Dasgupta, and they provided the following bounds. For K-means and K-medians, they have a log K lower bound, and for K-means K-square upper bound, and for K-medians a K order K upper bound. And here we contribute to this problem and to this area of explainability by providing new results. So the results that I'm going to present, for sure, they are not one of the deepest in this conference, but they should be one of the freshest results, in the sense that the paper was published today in arXiv. So I was working in the talk and in the paper together. So fortunately, I managed to match them. And it's together with a student of mine, a PhD student of mine. So for K-center, we have nearly tight bounds. For the maximum spacing, we have tight bounds. And for the K-means and the K-medians, we managed to improve the current results for low dimensions. So in the remaining of the talk, I'm gonna explain some ideas about these results. So this will be a technical talk, and I will start with the case center problem. So in the case center, we want to minimize. So we as the output, we should output case center, so that the maximum distance of a point to its closer center is minimized. This is the criterion for the K-center problem. Putting another way, we want to split the points into balls such that the maximum radius or diameter of these balls is minimized. Well, the case center is an NP-hard problem. There are constant approximations, but we are interested in the price of explainability. So maybe a first idea to come up with explainable clustering for case center is to consider this box that includes all the points. So here we have an example with 9 clusters. We want 9 groups, and it's in the 2-dimensional space. And we can do the following. We can divide this box into boxes of the same dimension. Maybe the picture doesn't help too much, but the idea is to have boxes of the same dimension. And in this case, we can upper bound the maximum distance from a point to its center or representative by the diagonal of one of these regions. It's very simple, and I'm gonna call it a grid strategy because we do this grid here. And the question is this a good strategy? And the answer is no, it is not a good strategy to obtain explainable clustering. In this example here, in the same region, we have points that are far from each other if we compare their distance with the optimal unrestricted clustering. So the cost, if we use this strategy, the cost of explainable clustering is very high compared with the optimal unrestricted one. In fact, it can be arbitrarily bad. But this idea of, this grid strategy, it may be helpful. We need to refine it a little bit. And for that, let me introduce this concept of what we call by a cut mistake. So imagine that we start with the optimal unrestricted clustering. So each group has a different color, and the center is represented by a square. And we want to have explainable clustering. We apply a cut here, one of these cuts. And this cut will separate some points from the reference center. Here we are separating 4 points here and 3 points here, 7 points. So we are making 7 mistakes. And this is a cut mistake. And to refine the grid strategy, we can do the following. We start with with k reference centers. They may be the optimal solution, the optimal centers in the unrestricted clustering. And as long as we can apply a cut that doesn't make mistake, we apply it. But at some point, we may reach a node in the decision tree where there are no mistakeless cuts. So every cut makes a mistake. And in this situation, we apply this grid strategy. And the consequence is the following. So here is a situation where there is no mistakeless cut. So every cut here makes a mistake. Every cut that we try will make a mistake. So in this case, what happens is that we can have a lower bound in the optimal unrestricted clustering. It's given by an expression like that depends on the sides of the box and on the number of clusters. But if we compare this bound with the diagonal bound, we have a factor of square root of k. So using this refined grid strategy, we have this upper bound of square root of k for dimension 2. And the same idea can be applied for for higher dimensions, exactly the same idea. And then we have a bound like that, square root of d times k to 1 minus 1 over d. But then the question is this a good bound? Is this bound is tight? Is this a good characterization of the price of explainability? So let us investigate an instance in 2-dimensional space in order to answer this question. So, okay, I'm giving this example here. So let us assume that we want 16 clusters. And in order to build this instance, we first define some special points that they will be centers in our solution. They will be centers. So here we have these 16 points. They are obtained through this formula here that it's not important right now. But the important property is that the distance between any of these center points, it's something like square root of k. So this formula guarantees something like that. The minimal distance is square root of k. And in order to complete the instance, we add some points close to each of these center points. So these points are identical to the center points in all coordinates but one. In one of the coordinates, they are different. So this is the construction. And from this construction, well, the first thing that is, is a direct consequence is that the optimal K clustering, the cost of the unrestricted clustering is just 3/4, because each of these structures is a cluster. But how about the explainable clustering? Well, what happens here in this construction is that we don't have mistakeless cuts. So if we try this cut, it makes a mistake. If we try this cut, it makes a mistake. And what is the consequence? The consequence is that one of the points will be separated from its original center. And we will be forced to assign this point to another center that is at distance at least square root of k. So the consequence is that any explainable clustering for this instance has cost at least square root of k. And then we have a sharp characterization of the price of explainability for dimension 2. Okay, and how about higher dimensions? Well, we can extend these constructions for higher dimensions. I will not, of course, provide all details, but just give the flavor. The idea is the following, which is basically somehow we look to that formula and then we try to understand what was going on and then we extend it. That was the idea. So we define a parameter P that depends on the number of clusters and on the dimension D. And we also define a base using this formula here. And we want to define these special points, the centers. And we use this we use this procedure here. First, we obtain a base B representation of number I. And then we need to define the coordinates of center I. And for the first coordinate, we use one circular shift of the I representation. For the coordinate 2, we pick the base B representation and we apply two circular shifts. And up to coordinate P, where we apply P circular shifts. So this is the construction. But to define a center, we are in dimension D, and we just defined P. And then we repeat the procedure for the remaining coordinates. And at the end, we add these associated to each center, we add 2D points. So these are the points that were surrounding the center point in the 2D construction. So this is the construction. And analyzing this construction, we obtain the following bounds that for this small, and by small, I mean smaller than log k over log k, we have this bound here. And for the larger than this threshold, we obtain this kind of ugly formula here. But in terms of tightness, well, this bound is tight for constant dimensions by tight up to constant factors. And the gap between the upper and the lower bound in general is little o of log of 1.52k. So the gap is somehow small if we compare to the magnitude of the upper and the lower bound. So in this sense is, I mean, it's, let's say, nearly tight. Of course, there is room for improvement. Okay, so this is the first problem that we consider, and now I'm gonna move to the k medians, which is so the k center is the criterion is an worst case criterion, and now in k median we want to minimize the sum of the L1 distance from the points to their representatives. So this is also a popular criterion. And this was one of the results that was investigated in Dasgupta paper. And they proved that the price of explainability for k-medians is at most order of k and at least log k. And a nice aspect of this bound is that it doesn't depend on the dimension d. For the bound that we get for k center depends on the dimension d. Okay, I'm gonna explain a bit how they get this upper bound because we're gonna use some of the techniques. Good. So we want to build a decision tree that is explained. I mean that provides an explainable clustering that is good with respect to the k-median criterion. We start with the optimal unrestricted clustering. And maybe it's, well, we cannot compute in polynomial time, but we can approximate in polynomial time if we are interested in polynomial time algorithms. Okay, and we're gonna apply a cut here. This cut will separate the points into two regions. And here it makes some mistakes. And yeah, this cut is making 6 mistakes. And then we'll not be able to assign these points here to their original centers. And then we have to assign it to some center. And this center may be anywhere in this bounding box here. So we can compute the excess with respect to the optimal solution of this node. So this node, because of the cut, it's yielding some excess with respect to the optimal solution. And a way to compute this excess is to multiply the number of mistakes by the diameter of this bounding box. And then we split the node into 2 new nodes. So the right node here. And then we apply the same, we apply a new cut. It makes 1 mistake. And then we have an excess associated with this node V. Okay, and we can apply the same idea for every node. And at the end, we have this upper bound on the cost of an explainable clustering provided by this decision tree. So it is at most the cost of unrestricted one plus the sum of the excess of each node. And this excess is given by this formula here, the number of mistakes times the diameter of the node. And given this expression here, a natural idea is to try to minimize the number of mistakes at each node. So this is a greedy strategy. And this is exactly the strategy proposed by Dasgupta paper. So they have a greedy strategy that minimizes the number of mistakes at each node. They can do it in polynomial time. Consider all the cuts. So many of them are, there are many of them are equivalent, and they pick the best one. Okay. So they have this order of k upper bound, and yes, they managed to compare it with a lower bound, but I will not explain how. There is no time to explain the ideas. But we are interested. So this, as I mentioned, this bound is independent of the dimension. But well, if we think about what happens in dimension 1, if we want to have an explainable clustering in dimension 1, the price of explainability is 1, because the explainable clustering and the unrestricted clustering are the same. So we want to investigate what happens when D is small. So can we improve this bound if for low dimensions? And to do that, we go back to this formula here, that is an upper bound on the optimal explainable clustering. So this is the excess of D, the excess with respect to the optimal restricted clustering. And we can decompose this excess into the different dimensions, because in the L1 norm is just a sum for each coordinate. This is what we are doing here. And let's call it this. This is the excess. This is the, let's say, the contribution of a single coordinate to the excess. So this is the basis for our approach. So what is our approach for building an explainable clustering? So it is a two-step approach. So first, for each coordinate I, we build a decision tree that is specific for this coordinate. So this decision tree tries to optimize the excess of this coordinate, and it completely ignores the remaining coordinate. And then at the end, we're gonna have the decision trees, one for each coordinate. And then we build a final decision tree by selecting nodes from these decision trees. So that's the idea. It's a two-step procedure. So I'm gonna give some idea or explain, give some details of how we build this decision tree here, and then how to merge them, or to pick the nodes of these decision trees to obtain the final tree. So just in terms of bounds, what happened? This first step includes a factor of log k, and the second step incurs a bound of D. And at the end, we have that the price of explainability is at most D log k, which is an exponential improvement for low dimensions. I would love to cut this factor here, but I don't know how to do it. And but so this is the result. Okay, so about the tree that is specific for a coordinate. So let's we have here a 2D example, and let's build a tree that is specific for coordinate x. So this tree will only use cuts for which x is fixed. It uses this kind of cuts here. Then at the end, we have a decision tree with, let's say, this face. For the other coordinates is the same. But we don't use any cut. So we also restrict the values that we can use here. And these values here, for which we fix the coordinate, let's say x, we look to the centers of the optimal unrestricted clustering. And we only set values that are given by the midpoint of 2 consecutive centers. So we sort the centers of the optimal unrestricted clustering with respect to coordinate I, and then we can only fix our cuts must have a value that is equal to the midpoint of 2 consecutive clustering. Okay, let's move on. And the key observation, we are trying to minimize the excess of coordinate I with respect excess with respect to a coordinate I, which is given by this formula here. But this problem, it can be connected or even reduced to a problem of doing binary search in a totally ordered set of items where each item have a distinct search probability and probing cost. So there are many papers about binary searching, variations of binary searching where there are non-uniform testing costs or different access probabilities, and in fact much more. But we can reduce to one of these problems here. And just the reduction has to do with the items will correspond to the cuts. The probing costs will correspond to the number of mistakes. And the search probability has to do with the distance between 2 adjacent centers when we sort along coordinate I. So this is the kind of reduction. Okay, but so then how we build the tree? So we use these competitive trees that were proposed in a nice paper by Charikar at Stock 2000. And the property of these binary search trees is the following. So the property is that there exists a binary search tree for k items. So each item is associated with a node, such that the cost of finding the node j, the item j, is at most log k times its probing cost. So if an item j has cost 1,000, we pay at most log k times 1,000. So this is the kind of result. So this is for search trees with non-uniform testing costs. And so the tree that we use for coordinate I is this competitive tree given by Charikar. So by Charikar paper. So for each coordinate I, we use a competitive tree. And the implication is that the cost of this competitive tree will be at most log k times the contribution of coordinate I to the unrestricted optimal solution. So the log comes from this analysis. Okay, so this is our first step. We build a tree for each coordinate, and we are paying a factor of log k. And then we have a lot of trees, different trees, and we have to build a final tree, picking nodes from these different trees. And in order to build the final tree, the only thing that we have to define is which cut we use for each of the nodes of the decision tree. So let's consider a node U. We want to define the cut, which cut we use for this node U. And we look to the bounding box. There are two, one side is dx and the other side is dy. So the first thing that we decide is which coordinate, which of our trees from the first step we use. We're going to use one of these trees. Which tree we use? And then we're going to, so one possible criterion, there is more than one, that then we get different bounds, is to consider the coordinate I for each this side is maximum. So here we have let's just two sides. So if dx is larger than dy, we pick dx. So we pick the coordinate associated with the maximum side. So this will be the tree. And now we're gonna pick a cut from this tree. Okay, so how do we pick this cut? So we consider the centers of the optimal solution that lies in this node U. So some nodes, some centers of the optimal solution by construction will reach this node U. And then we take the least common ancestor of these centers here in the 3DI. So we look to the optimal centers that reach this node, look to the least common ancestor here. And then we apply the cut given associated with this node here. That's what we do. And then we pay a factor of D for doing that. As I mentioned, there are other criteria to do that. And by using other criteria, we can obtain the same bounds and also recovering the result from Dasgupta paper. It's also possible to do that. Okay, so and this is, I hope I managed to give some ideas of the flavor of the result. And the consequence is the price of explainability for k-medians is d log k. It is an exponential improvement for constant dimension, as I mentioned before. The same algorithm with basically the same algorithm can be adapted for the k-medians criterion, and then we get that the price of explainability is dk log k. So there is an extra factor of k, but still is an improvement for low dimensions with respect to the k-square bound. Let me say some words about the other criterion, the maximum spacing criterion. So here we have a maximization problem where we want to maximize the spacing, and the spacing is defined as the minimum distance between points in different groups. So here, this is the spacing. Okay. Well, here, like the good news is that we have a tight characterization of the price of explainability, which is n minus k. And the bad news is that this price is very high. It depends on the number of points. I mean, it's not the kind of result that we would like to have. Okay, I will skip. I mean, the lower bound is a very simple instance, and for the upper bound, we start with an optimal solution and make use of this optimal. Try to modify this optimal solution using something similar to Kruskal algorithm. So this is the idea. Well, I think I'm approaching the end of the talk. So some final remarks. So in this research, we presented new efficient algorithms for building explainable clusterings. During the talk, I was always starting with the optimal solution, and for many of the problems, the optimal solution cannot be built in, let's say, polynomial time, but it can be approximated in polynomial time. So we can get efficient algorithms. And we have also new bounds and characterizations on the price of explainability for popular objective functions. And I believe this could be helpful to, if one has to decide one criterion when explainability is required. This shows, I mean, this gives some idea of the potential loss. So it may be helpful in this sense. About some directions, I think there are interesting theoretical questions that are open. For instance, tighter bounds or tight bounds for k-means, k-medians, and even k-centers. Another direction is approximation algorithms. And because here we were comparing with the optimal unrestricted clustering, but one can try to compare the solutions with the optimal explainable clustering. And I can think also about complexity results. In terms of explainability, I think that there is room for many other models. I mean, for instance, decision trees with limited height. The height is a natural measure because it has to do with the length, the size of the explanation. So it makes sense to try to minimize the height, avoid large height. There are some results when a recent paper where a cluster can be associated with more than one leaf. So here we lose some explainability, but we can obtain, we can improve the objective function. So that's the idea, trade-off. Can think about alternative measures for the price of explainability. And there is room for also experimental results. There is another paper by Dasgupta where he makes experiments, and the result is that these explainable clusterings are not, I mean, they are kind of close to the unrestricted one. There is a paper by Bert Simas using integer programming to solve this problem. So this is another area where one can try to, to invest. So that's all. Thank you for your attention.
So thank you, Eduardo. Let's thank the speaker. So maybe we can unmute everybody. Guilherme, maybe. Better. Okay. Thank you, Eduardo, again for the nice talk. So there are some questions that came during the talk. So I don't know if Gonzalo wants to ask the question himself. There was a question from Gonzalo.
Yeah, I can start. Hi, Eduardo. Nice talk. I wanted to ask you if there is anything known about what happens with the language of what you can put inside the nodes of the binary decision trees. Because right now you're considering only that some coordinate is smaller or larger than a constant. What if you can write xi is larger than xj, for example, which looks like explainable to me?
Yeah, yes, this is I think it's a good question. At some point, I mean, I didn't invest on something like that, but I thought instead of just a test, you can have a hyperplane with two, as you are proposing. And yeah, it should have a trade-off. Probably we can have better approximations. And if it's still explainable, even better. I think it's a nice direction. Did I answer your question?
Well, so you mean nothing special is known about that at this point?
As far as I know, yeah, okay. I don't know results about that, at least in terms of theoretical results.
Okay, okay.
Right. So I just wanted to pitch in. So these are what you are describing, Gonzalo, is a special case of linear decision trees, I believe, where in linear decision trees, you can have any linear function and you can branch along that. And it seems like the machine learning community briefly considered this, but they seem to have like lost the, because I think decision trees were not very popular. So linear decision trees they lost their popularity very soon. But I think it's very interesting and worth exploring.
Okay.
Yeah, I think the interesting point about Gonzalo, yes, there are, when I mentioned that I don't know the result in terms of explainable clustering, but maybe with two variables, it's still explainable, and I think it's a good point.
Yeah, right.
So there's another question by Lucas. He asked a question. Do you want to ask the question yourself, or it was?
Hello, can you hear me?
Yeah, fine.
Okay, so I think this question was kind of answered when you talk about higher dimensions, but I have another question that I would like to ask. My question is if you have studied if there is a way to decrease this upper bound, or how much can we increase it? How much can we decrease this upper bound if we increase the number of leaves in the decision tree that we are using as an explanation? Even if we increase it slightly, like keep it a small size. But I asked this question because I think the number of leaves equal to the number of clusters is kind of conservative, kind of small, right? And I mean, in practicing of this, we usually use much bigger trees.
Oh, yeah, so I think that one of the papers that I mentioned, I think this paper here by Frost et al. So they do exactly this. I mean, I'm not sure that they improve. I don't think they improve the bounds, but they allow more leaves, more than K leaves. And in terms of experiments is better. In terms of the bounds, I don't think that they managed to improve, but I would have to double check. So I think this is, sorry, the reference is not perfect here, but I can provide you later.
Okay, that is great. By the way, thanks for the presentation. It was awesome.
Thank you very much.
Okay, so there is another question. Hilton, please.
Hi. Thank you, Eduardo, for the talk. In fact, I have two quick questions. The first question is, just to make sure that I understood correctly, is that your upper bounds give algorithms. So say if I give an unrestricted clustering, then I can get the explainable clustering from your proofs, right?
Yes.
So that's it. I mean, that's kind of an algorithm, the upper bound.
Yeah. It's not just existential. It is an algorithm.
Okay.
Yes.
Okay. The other question is about, I mean, do you think these results can extend to different kind of clusterings? Because I'm particularly interested in the facility location kind of clustering, because in which instead of having K clusters, you have some cost to create each cluster. So you don't know the number of clusters that you end up with, but you have some kind of cost to control the number of clusters. So do you think that you can kind of extend this proofs to these other kinds of clustering?
Well, this is difficult to answer. Yeah, maybe if we talk later and you explain me more, maybe I can say something useful. But right now, I'm sorry.
Oh no, thank you. I was just wondering. Thank you very much.
Okay, thank you.
So, are there other questions? Any other question? We have just a couple of minutes, I think, still. Or if not, I have. It was about 50 minutes, I think, the talk, the net of the talk, I think. I have a question about, you define the explainability with respect to, so what you have is always an approximate algorithm, so a polynomial solution. I mean, what about the explainability with respect to the best possible you can get? Would it make sense?
Tell me again, sorry.
So because the lower bound is the best possible, it's also not necessarily polynomial, but the upper bound is always polynomial, right? Or are you defined with respect to the best possible decision tree you can get? Also in exponential time.
Oh, yes, no, so...
maybe I missed something, sorry, I missed something.
Maybe here, sorry, it's a big talk, lots of slides. Well, here I don't know whether, here we don't care about the, if it's polynomial time or not.
Right.
Okay, so having exponential time, I don't know how to use it, but in this definition, you are allowed. But if you can come up with a polynomial time algorithms, even better. But here, is this the question?
Yeah. But the results are always for polynomial time algorithms, right?
Yeah, all the results we obtain polynomial time algorithms. Yes.
Yeah. Right. So my question was whether the ratio in the case of non-polynomial time algorithm could be better than what you're given.
Well, yes. So I was not really concerned to come up with. I mean, yeah. When we look to this definition, like the time efficiency is not something that we are really interested. So if you have a bound that is better, if you have a better bound using exponential time, it's okay. It's good, because maybe there is a separation between the kind of bound that you get using polynomial time and exponential time. And then it's like the results using exponential time, I think they are interesting because they show that explainability cannot be some limit for explainability. But of course, obtaining polynomial time is always interesting.
Okay. Thanks. So are there other questions? Well, if not, then let's thank Eduardo again, and then we can, so. I think